Alrighty then, I wanted to go over the quiz so you guys would have access to the correct solutions here. Okay, let's do this. I will also give you a hard copy, I guess an e-copy of the PDF here of the solution. So I'll scan this later. Anyway, let's look at number 1 here. You should have looked at this. Consider the arrow diagram or map for the function f below. 1 maps to 2, 2 to 3, 3 to 5, 5 to 1. Okay, so there we've got that. Is this a one-to-one function, yes or no? Well, the idea is what? The domain is the set 1, 2, 3, 5, all right? And the range is 2, 3, 5, 1. They're actually the same set, right? Okay, is it true that corresponding to every element of the domain, there's only one element of the range and vice versa? And the answer is yes. You can see I could actually turn the direction of the arrows there, and I would also have a function. So yes, this is indeed a one-to-one function. Draw an arrow diagram for F inverse, okay? All I'm basically going to do is take this same arrow diagram, or map, if you like that word better, and first of all, I'm going to write I'm just changing the direction of the arrows. Together with one other little point here, what I'm going to do is use the convention that we have the domain on the left-hand side. So we go domain here and the range here. Okay, don't forget your little arrowheads on these. Let's see, 1 was pointing at 2, so for the inverse, 2 would point at 1. Okay, 2 points at 3, so 3 would point at 2. Okay. 5 would point back at 3, and 1 would point back at 5. So there's F inverse right there. That's all there is to it. You could imagine if I was writing these as ordered pairs, like 1, 2, 2, 3, 3, 5, 5, 1. All I would be doing essentially is what? Switching the ordered pairs. Okay, switching the order of the elements that appear in the ordered pairs, maybe. Okay. Draw an arrow diagram for F composed with F inverse, okay? Now, if you guys think about this, if you're going to compute, F of F inverse of, some value X, you're actually going to be computing what? F inverse first. Because we read from left to right, that means you're actually going to have F inverse up here first, or on the left-hand side, I should say. Okay, so I'll write that again. All right, so there's F inverse again. Then I'm going to write F second because it's actually the second thing that gets computed. So just transcribe that. Very simple, just a copying exercise. Okay, and 5 points at 1. Now to compose these, I'll write that at the top here. F composed with F inverse. So here comes the arrow diagram for that. All I do is basically what? Follow the arrows out. So 2 points at 1. Okay, you could say then that what F inverse of 2 is actually 1. And then that drops into F. F takes 1 and turns it back into 2. So 2 goes to 2. Do you remember with composition, with arrow diagrams, you're just following the arrows. Okay? So 2 goes to 1, 1 goes to 2. So ultimately 2 goes to 2. 3 goes to 2, but 2 goes to 3. So ultimately 3 goes to 3, goes back to 5. So that means 5 goes to 5, 1 goes to 5, goes to 1. Okay? So there's the composition. I'd like you guys to block in your final answers here, or circle them. So let's go ahead and do that. I guess I could have done that right here as well. There we go. All right. Not that I would probably get mixed up on something like this, but there it is. Okay. All right. So there's the composition. What do you notice? This is actually an example of an identity function, right? Every element in the domain of F inverse points, which is the range, of F, actually points to itself, doesn't it? Now, what if I was to reverse this and have F inverse composed with F? Well, I actually have to compute F first. So I'm going to write F on the left-hand side, or first if you're reading from left to right. Okay. And then I'm going to have F inverse on the right. So that's looking like this. Okay. Now let's go ahead and compose this way. So I'm doing F first. 1 drops into F and 2 pops out. That 2 pops into what? F inverse, and 1 comes out. Okay, so ultimately F inverse composed with F means 1 goes to 1. 2 goes to 3, goes back to 2. So 2 goes to 2. 3 goes to 5, goes back to 3. 5 goes to 1 to 5. Okay? Okay, so there's another identity function. Remember, whenever you're composing a one-to-one function with its inverse, you get what? You get an identity function of some kind. In fact, this time, because the domain and range were exactly the same up here, which is not usually the case, right, with most of our functions, these actually end up being what? Exactly the same function. Do you guys see that these are exactly the same function? That doesn't usually happen here. All they are is written in a different order. It's still the same function because 1 points at 1, 2 points at 2, 3 points at 3, and so forth. Okay, well, there's the answer to number 1. Okay, but you should be able to compose functions like this or with what? Ordered pairs. Okay, and if you need to compose with ordered pairs, it's just about as easy, but if you want to create an arrow diagram from it and follow the arrows. Okay, what's the implicit domain of this function? Okay, what is implicit domain? Well, we're only working with real numbers now in this chapter. Okay, true, we've studied complex numbers before, but we're ignoring those again. Okay, we'll pick them back up again in the next chapter here. Implicit domain of the function means this: if you've given a function by a formula, it's the set of all real values of x that you can plug into the formula and have that make sense in the real numbers. Okay? Alrighty? Now we're going to see there's some exceptional things going on here. Okay? Look at down here. Let's maybe look at that radicand, x plus 3. I just want to make a comment. X plus 3 is what we call a polynomial, right? We'll discuss more of that in the next chapter. But the domain of a polynomial is all real numbers. Okay? Nothing can go wrong. Think of x plus 3. I can add 3 to any number and I'll get an answer, right? Okay, there's no problem there. However, what am I doing? So x plus 3 isn't a problem, but what am I doing with that afterwards? I'm taking its square root. Now remember, I'm dealing only with real numbers. There are some numbers you can't take the square root of and get a real number answer. Which numbers are those? The answers are negative numbers. Okay, negative numbers. So here's what we have to actually have here. We have to have, I'm going to describe the domain this way. It's the set of all x such that x plus 3 has to be positive or 0. So I'll write greater than or equal to 0. That just means non-negative, all right? Because otherwise we're okay. Okay? So long as x plus 3 is positive or 0, we can take the square root. Okay? There is another problem that creeps into this function, though. Because we're taking a quotient, we're dividing here. I'm dividing by x. There is a number I can't divide by here, and that is x equal to 0. Remember, that denominator better not become 0. If the denominator is not 0, then you're okay. You can divide. But if it is equal to 0, then you're in trouble. Okay, where is it equal to 0? Okay, where is it equal to 0? Well, it's 0 because it's such a simple, polynomial. X is also a polynomial. It's a really super simple one. Okay, but anyways, you have to have x is not equal to 0, and you'll be fine here. So the domain of this function is a set of all values of x that satisfy this condition and satisfy this condition. Okay? Now, if you think about it here, let's do a little scratch calculation here. This means x has to be greater than or equal to negative 3, just subtracting 3 on each side, and x cannot equal 0. if I was going to write this on the real number line, greater than or equal to -3. Now, because of that equal sign here, I've got a filled in dot, right? And then I would do what? I would shade everything this direction. But whoops, stop here. I got to punch a hole where? At 0. I got to kick 0 out. I can't hit 0 in there. Okay, so that's the real number line. X, okay? So do you see what the answer is? Okay, in terms of interval notation, this would be what? Square bracket -3 up to 0. Parentheses, because then I want to include 0. And then what? Because it's two different sets here that I've got to put together in one, I take the union. And again, parentheses from 0. No limit to the right, so that goes out to infinity. Please box in your final answer. And then I can see precisely what you're asserting here. So there is the domain of that function, or some people will call it the implicit domain. Okay? Implicit just meaning hidden. Okay? Now, let's look at this. We've got a piecewise defined function. We're calling it h of x. H of x is x squared if x is less than -1. But it changes definition depending on which interval it's in here. It's actually just what? 3x if x is between -1 and 2, actually when it's equal to -1 also. And then what? From between 2 and 4 inclusive, the function is defined to be x cubed. So if you were to graph this thing, you'd have a piece of a parabola, then a piece of a straight line, then a piece of a cubic here. Okay? Alrighty? Alright. Let's go h of -2, right? I'm evaluating this function at -2, nothing more. Well, my x value is -2, right? Okay, x is -2 now. Now just run through the test here. Is -2 less than -1? Or is it between -1 and 2? Or is it between 2 and 4? Which of these applies here? It's actually the first one. -2 is less than -1. So the function there is defined to be what? The square of the x value. My x value is -2. So I've got -2 squared, and I've got 4 for my final answer there. Okay? How about h of -1? Okay? Which interval does -1 fall in? This interval? I should be pointing over here. This interval? That middle interval? Or that last interval? Where does -1 lie? Does it lie in any of those intervals? Maybe it's not even part of the domain. Actually, it is. It falls in this interval right there. Okay? So my function is defined at -1. Because it falls in this middle interval, I've got to use this middle formula when computing the value of h. Okay? H is just 3 times whatever I put into it when I have what? A value of x between -1 and 2 there, including -1. So this should be what? -3. How about h of 0? Which interval does 0 lie in? The first one? The second interval? Or the third interval? Does it lie in any of these? It actually lies in what? Oh, the second interval also. Well, the function there is 3 times whatever you put into it. 3 times 0 is 0. How about h of 2? 2. Is it in what? The first interval, second interval, or third interval? Well, now that's a less than 2 sign, right? Less than sign. Okay? 2 is less than or equal to x, so actually the formula what? It's the third interval that 2 lies in, so our formula there is actually the cube of whatever you put into it. So I would be cubing 2. 2 cubed is 8. So there's my final answer for that one. Now, h of 4. What? 4 lies in the third interval. So once again, I would be cubing what I put into it. 4 cubed is 64. Now let me throw in a question that I did not ask here. What would be h of 5? The answer is h of 5 does not exist. 5 is not part of the domain. Notice that 5 doesn't lie in this interval, the first one. Doesn't lie in the second interval. It doesn't lie in the third interval either. And this is the only way the function is defined. So 5 is outside any of those intervals. 5 is outside the domain. So h of 5 does not exist. Okay? This brings up this question. What actually is the domain of h of x in interval notation? Now, this is going to be very easy, actually. All you're going to do is write each of these intervals you're given here, and typically they're intervals. It could be at just a single value, actually. Well, I guess that would be an interval also, technically. So anyway, look at the three intervals. Let's look at the first interval. What is that in interval notation? Less than, strictly less than -1 would be from -infinity to -1. Because it's a strict inequality, I'm going to use parentheses. I'm not including -1. Okay, the next thing to do, take the union, look at the second interval. How do you write that in interval notation? Where you're going from -1 to 2, you are including -1, but you are not including 2. So I'm going to use a square bracket at what? -1, but only parentheses at -2. And then I'm going to go union this last interval from 2 to 4. I'm including both 2 and 4. Okay? Now we want to write our answer in the simplest possible way. Technically this is correct, but can you see here what I'm doing is going from what? -infinity out to -1. If I was to just graph this by itself, that's what it would be. But then I'm going from what? -1 to 2. I'm including -1, so that gets filled in. I'm going all the way out here to 2. Okay, so let's say here's 2. That's open because I've got parentheses there, right? I'm not including 2. Okay, but on this interval, I'm going from 2 to 4. Notice I'm including 2, so that gets filled in. Everything out to 4, I'm also including 4, so that gets a solid or filled in dot. Notice that I've got what? Everything less than or equal to 4 then, right? That would be the set I'm talking about. So this actually boils down to -infinity, so 4, and maybe I want to put that in here where I'm supposed to answer the question. Okay? I'll box it in here for the sake of consistency, but I wouldn't have gotten mixed up in that part anyway. All righty? All righty. There's problem 3. Let's look at problem 4 here. Okay? All right, I'm going to be doing some composing of functions here. Okay, so g of f of x, or g composed with f of x, means the same thing as this. Okay? All right, now what's f of x? F of x is actually the square root of x plus 3. So in place of f of x, I'm putting in that formula, the square root of x plus 3. Now, here's something I want to emphasize here. Don't get hung up on the fact that g is written in terms of x here. It could be g of z equals z squared minus 3, or g of y equals y squared minus 3, or g of apple equals apple squared minus 3, right? It doesn't matter about the variable I've written it in. What matters here is really what g does to what you put into it, right? A description for g of x would be, excluding, x. A description for g is it takes whatever you put into it, squares it, and subtracts 3. Okay? So think of it that way. So what am I going to be doing here? I'm going to be squaring the square root of x plus 3 and then subtracting 3 from that result. Now, the square of the square root of x plus 3 is x plus 3. And then I'm going to subtract 3. So I'm going to get x for my final answer. Okay? Now let's turn this around here. I've got f of g of x. Okay? Now there's a surprise on this one. People often make a mistake on this part. Okay, what's my g of x? My g of x is x squared minus 3. And again, don't worry about the fact that f is written in terms of x. What matters is what it does to what you put into it. Now, what am I putting into it? X squared minus 3. What does f do to what you put into it? It takes whatever you put into it, in this case x squared minus 3, adds 3 to it, and then takes the square root of that result. Okay? Alrighty, so this would be the square root of x squared, which is what? Actually, it's not x, it's absolute value of x. Do you guys remember that? Okay? Yeah, if x is negative, for example, negative 7. Negative 7 squared is 49. The square root of 49 is 7, not negative 7. You get a sign change when you put a negative number into this. Okay? That does not happen up here, by the way. Okay? So go ahead and remember that. So remember that the square root of x squared, if you're dealing with real numbers, x has to be greater than or equal to 0 anyways, but that ends up being x. But x can be negative here. The square root of x squared is absolute value of x. Okay? I just want you to note that, so we'll put it down here. Okay? Alrighty. Find non-trivial functions f of x and g of x such that f composed with g, let's maybe write it this way, is the cube root x squared plus x plus 1. Now this is useful in calculus. You have to be able to understand a composition and decomposition. Okay? Probably the easiest way to approach this thing would be the following. Let's go ahead and have, I'm going to call this the inner function, okay? Or think about what you have to actually compute first. Now I want to see this as just a composition of two functions. I could actually see it as a composition of more than two functions, but I'm just going to try to see it as two functions. I have an inner function and an outer function, f. The inner function, or what I'm calling g of x in this expression, is the function I have to compute first. Now, if I gave you a particular value of x and I asked you to compute this, okay, compute this composed function, the cube root of x squared plus x plus 1, what would you do? You would probably do the following. Well, you would have to do the following. You would probably compute first the inner function, x squared plus x plus 1. And then what would you do? You'd take that result and you'd drop it into the cube root function. That's the second one that gets computed. So this would be our composition, or decomposition. Okay? Are there other ways to decompose these functions? There are, in fact, other ways to decompose these functions. Here's another example. Oh, by the way, this example is the most reasonable, and this is the most useful in the calculus. Here's another way, for example. I'll just write e.g. for example. We could have this, f of x. Let's maybe write g of x first. Okay. X squared plus x, and f of x is the cube root of x plus 1. Okay? Now f of x does what to what you put into it? It adds what to whatever, 1 to whatever you put into it and takes the cube root of the result. If I dropped x squared plus x into it, what would it do? It would dutifully add 1 to that and take the cube root of the result. That's exactly what I have here. Okay? Okay, so we're not saying decompositions are unique. Okay? But this is the most useful one right here. It's the one that's most logical, and it's also the most useful in the calculus. So this is my preferred solution here. By the way, when I mention non-trivial functions, that means you don't have any functions that are actually the identity function. Some wiseacres did that in the past. F of x equals x, and g of x is the original function. You know, that's a trivial decomposition, so you're not going to get credit for that. Okay, very clever in the beginning, but it's not going to help. What's the average rate of change of a function? Do you remember this? Okay, if I have y equals f of x, the average rate of change, remember this in the book and videos? That's a very easy idea. It's actually slope of the secant line to occur between 2 points. But let's talk about the average rate of change is the change in y. Have you seen that before? Delta, change in x. Okay, change in y divided by change in x. So this actually represents a slope. But here's what we'll do here. Okay, we'll go ahead and say, what's my x value? Okay, I'll start with the larger one. I'll go from larger to smaller. But it doesn't really matter so long as you take your differences in the appropriate order. Okay, and then I have my f of x value. Okay, let's see. The value of x is 5. That's my second or larger value. If I stick that into the function and evaluate, I get 5 squared is 25 plus 3 is 28. Okay. If I stick 1 in there, I would get what? 1 squared plus 3 is 4. Okay? All right. Now, can you see what the deltas are? Okay? These are the changes. Okay? Can you see delta x is 4? Delta y is what? 24. Okay? So delta y divided by delta x is 24 divided by 4 is 6. Okay? Okay? Okay, there's the average rate of change. Let's talk about some shifting here. Okay? Now, I'll express something here in a little bit here. But if you look at your sheet here, I've actually gotten a lot of formulas written in terms of level curves rather than formulations like this in the book. Okay? But here's the idea. If I've got y equals, let's try this, y equals f of x minus a plus b. Okay? This is how it's often written. Okay? Have a minus sign in here to get this correct. Okay? By the way, this is consistent. If I subtract b on both sides, I'd have y minus b on this side. But this is the idea. This is going to be shift a units in the x direction, or horizontally. And then what? B units in the y. Okay, so we're looking down here at this. Okay, keep this in mind here. Okay, what's my a in this case? My a is a positive number. It's 2, right? My a is 2 correspondingly. Okay, a is 2, so that means 2 units in the x direction. Now your book and other people will often, and it's on the exam this way, what does it mean 2 units in the x direction? That actually means 2 units to the right. The right is the positive direction, right? But some people express it differently. Like sometimes I'll just say shifted 2 units in the horizontal. That means 2 units to the right. Had that been negative 2, that would be what? Shifted negative 2 units, or what? 2 units to the left. Okay? Negative 2 units or 2 units to the left. But that doesn't apply in this case. Okay? Let's go. And what's my b here? My b is 3. So this is going to be 3.
Okay, the last video got cut off halfway, so I've got to continue here. All right. I didn't realize that at that point. Anyway, so this ended up being shifted 2 units to the right and 3 units upward. Okay. To compress the graph, y equals f of x by a factor of 1/2 in the x direction, and stretch by a factor of 5 in the y direction. What would you do? Well, stretching in the y direction is probably the easiest thing to see here. Okay, what you would end up doing is multiplied by a factor of 5. Okay, now what you want to do is take the reciprocal of the half and stick that, which is what, 2 over 1 or 2? You want to stick that on the x here, and that will give you actually a compression by that factor of 1/2 here. if you look at the sheet. By the way, just for the consistency here, you see if I divide it on both sides by 5, I would have y over 5. Y over 5 indicates a stretch by a factor of 5, okay? If that had been x over 3, that would be what? A stretch by a factor of 3. Always think in terms of the x, in terms of its reciprocal with regard to stretching or compressing, okay? In this, okay, so I've already got this done for you, unfortunately, because the last video got cut off. But here's the idea. You guys need to know this for the exam here. This is really good here. I've got a certain relation here in number 8 that I've written. X cubed plus 4x squared plus xy plus 2x minus 3y equals 5. And then I'm going to be reflecting it across what? The x-axis, the y-axis, and the origin, okay? The first thing I do is reflect across the y-axis. Now, the thing to do when you run into a problem like this is to create a little drawing of the xy plane and maybe put a point here. Usually I put it in the first quadrant, but it doesn't matter. Put a point labeled xy, and then reflect that across the y-axis. And you see I would be leaving the y alone, but replacing x by negative x. Reflect across the x-axis, and you can see I would leave the x alone, but replace y by negative y. Reflecting across the origin, I would go to the other side of the origin, and I would have negative x, negative y, okay? And this will tell you what to do to the relation and how you get its reflected relation, okay? Here's how you do it. In the first, so I got my equation for my relation. If I'm going to reflect across the y-axis, what am I going to do? I'm going to replace x by negative x, and I'm going to leave y alone. So that's all I did here. Okay, that's all I did right here and simplified. Okay, here for the x-axis, okay, if I'm reflecting across the x-axis, I leave x alone, but replace y by negative y everywhere. And don't forget your parentheses in here when you're doing your calculation. Some people mess that up sometimes. Okay, all right, and then simplify it a bit. Okay, and now here, when I'm reflecting across the origin, replace x by negative x and y by negative y. Again, don't forget your parentheses here when you go through this, like that. And then I simplified it here and put that on the line here. Okay, some people might multiply on both sides by negative 1 if you don't like a leading coefficient being negative, but it doesn't matter. Okay, so there it is. These are actually pretty simple. Just got to be careful. Okay, here where we're talking about even and odd functions here. Even function has the property that what? F of negative x is f of x, and an odd function is f of negative x equals the negative of f of x for all x, right, in the domain. The graph y equals f of x, where it's an even function, has what? Y-axis symmetry. This is because then you get the same function value over here, f of negative x, as you do f of x. That means these two reflected points across the y-axis both lie on the curve. Okay? Here, where it has an odd functions have origin symmetry. Okay? Here's the idea. If I was to have my original function y equals f of x, and think about taking like I did over here, it's origin reflection. I would replace y by negative y and x by negative x everywhere, like I've done here. But because this is an odd function, f of negative x is actually negative f of x, right? Then I could knock off those negatives on both sides and it'd be back to the original. This proves that an odd function will have a graph that's the same as its own origin reflection. That means it has origin symmetry, okay? All right, now here I just ran through each of these functions and replaced x by negative x and see if I got the original back. Here all the powers on x are even. It turned out to be an even function. Here I have even powers on the denominator, but an odd power on the top. G of negative x turned out to be what? The negative of the original. So that is in fact an odd function. This is just a collection of various even and odd powers here with that I called h of x. H of negative x turns out to be neither f of x, neither h of x nor the negative of h of x. So this function is like most functions, neither even nor odd. Okay, now to find the inverse of a one-to-one function, I promise the function I give you is one-to-one. I go y is my original function, so y equals 5x cubed plus 2. And then I interchange x and y, and then my last step is solving for y. So subtract 2 on each side, divide both sides by 5, and take cube roots. Okay? All right, so here's our final answer. F inverse of x should have been the cube root of x minus 2 over 5. Don't forget that 5 is underneath the radical sign, also part of the radicand. Okay? All righty. Last thing here, I've got the line y equals x, which is important for inverse functions, as we'll see, right? I've got the graph in red of a one-to-one function. You see it passes both a vertical and horizontal line test, so it's one-to-one. So it has an inverse. Its inverse function is g inverse of x. How is it related to the original? Well, graphically, what you can do to get the graph of the inverse function is to reflect the graph across the line y equals x, and that's what I've done here. Remember, when you're finding the inverse of a function, you take each ordered pair making up the relation or function, and you do what? You're just interchanging the two. That's exactly what happens when you reflect any point across the line y equals x. Okay, so there it is. I hope this helped.